Okay, so this will be the second lecture over chapter 17. So we'll just continue looking at reactions of aromatic compounds. So if we compared, so in this lecture we'll talk about this concept of OP versus meta-directors. So if we took toluene and benzene and this trifluoromethylbenzene and let them do electrophilic aromatic substitution and looked at the rate of those reactions. So if we assign the rate for benzene of 1, then if there's a methyl group on benzene, then it reacts about 20, that benzene ring reacts about 20 to 25 times faster than benzene would. So the ring is said to be activated, and CH3 is said to be an activator. Whereas if the CF3 is on the benzene ring, then that benzene ring reacts about 40,000 times slower than benzene. So the ring is said to be deactivated towards electrophilic aromatic substitution, and the CF3 group is said to be a deactivator because it makes benzene react slower. So further, if you do reactions, so if you had a CH3 versus a CF3 on the benzene ring. So if you start with toluene and you do the nitric acid H2SO4, that's the recipe to put a nitro on the ring. So now, of course, it matters where the nitro goes because all 6 carbons are not equivalent, right? So you could make the ortho product, or you can make the meta product, or you can make the para product. And so as you can see, you preferentially make the ortho and the meta isomer. So you get a 63% yield of ortho and you get a 34% yield of para, but you don't make very much of the meta isomer, only 3%. If you have a CF3 on the ring, however, then you preferentially make the meta isomer 91% yield, and you only make 6% and 3% of the ortho and para isomers. So the CH3 and CF3 group are said to be directing groups. They direct the next group that comes in to particular spots, right? The CH3 is said to be an OP director because it directs the nitro that comes into the ortho and the para position. And the CF3 is said to be a meta director, right? Because it directs the next group that comes in to the meta position, preferentially. So why is CH3 an OP director? And why is CF3 a meta director? So to answer that, we have to look at the mechanism. So what we want to do is for CH3, we want to consider the reaction at all 3 positions, the ortho, meta, and para position, and then we want to examine the stability of the intermediate, right? So that's the key point. Look at the intermediate, which one is more stable? So the one that's more stable is going to be the one that forms fastest, and so that pathway is going to be fastest, leading to preferentially those products. Okay, so if we look at the mechanism, so in the previous lecture, we looked at how HNO3 and H2SO4 react with each other to make NO2 plus your electrophile. So once you have the electrophile, if we let it react at the ortho position, then we take 2 electrons, make a bond from carbon to nitrogen, and that would put a positive charge on that carbon. And then if we draw other resonance structures, so let's take the next double bond and move it over, and then that would put the positive charge here. And then the next resonance structure, take the next double bond and move it over, right? So that's the farthest double bonds can go, from one bond to the adjacent bond. So if we move that double bond over, then this carbon becomes electron deficient, so now the positive is there. And then if we wanted to finish that mechanism, we would take the hydrogen on this carbon, and those 2 electrons would become a double bond there, and now you've made your product. So, but the point is, these are the intermediates. in that mechanism. So it's one intermediate. Those are the resonance structures of the intermediate. Okay, and so now if we do the same thing at the meta position, so if we take this double bond and let it react with benzene, then we put the positive charge there. That carbon is now electron deficient. And now let's draw resonance structures of that. So if we take this double bond and move it over, then now the positive charge is here. And then if we take the next double bond and move it over, then now the positive charge is there. So that would be the three resonance structures of that intermediate. And then to finish the mechanism off, right, the hydrogen where the substitution occurred at comes off, and those electrons are used to make your carbon-carbon double bond. So again, so that's your intermediate. So what we're going to do is compare these intermediates and see which one is more stable, and the one that's more stable is going to be the ones that form the fastest. Okay, and then if we did pair substitution, so again, let's take that double bond, make a bond to nitro. So now your positive charge is on that carbon. And if we move the next double bond over, so take this double bond and move it to that carbon, and now your carbocation is there. And then take the next double bond and move it over. And now your positive charge is there. And then to finish that mechanism, we'll lose that hydrogen. Those electrons will become that carbon-carbon double bond. Okay, so three intermediates, each with three resonance structures, but if we go and look at those resonance structures in more detail, which is the most stable? So what stabilizes carbocations? So if you remember for carbocations, stability is tertiary is better than secondary, which is better than primary, which is better than methyl. And all of these are allylic because they're all next to a double bond. So if we look at the ortho substitution, the key resonance structure is that one right there. Because if you notice, that carbocation is tertiary, whereas this is secondary and that's secondary. And for meta substitution, that carbocation is secondary, this one is secondary, and this one is secondary. So what is significant is that positive charge is never next to methyl. So it can never be tertiary. So the methyl group can never help stabilize it, right? So how does the methyl group stabilize it? Because the alkyl groups are electron releasing, so they help stabilize that positive charge. And if that positive charge skips the carbon where the methyl is at, then the methyl group can never help stabilize it. But if you did para substitution, then the key intermediate resonance form is that one. Because again, now the positive is next to the CH3, so the CH3 can help stabilize that positive charge by releasing electron density to it. So here that's secondary, this one's tertiary, that's secondary. So only when substitution occurs ortho or para to the CH3 can you get this tertiary carbocation where the CH3 can help stabilize it. So the ortho and para positions are going to be the fastest pathways because they have the most stable intermediate. Right, so basically it's, if you look at that on the energy diagram, so if you did ortho substitution or para substitution, then you can make this tertiary carbocation intermediate, and that's going to be more stable. If you do meta substitution, then all of the carbocations are secondary, so those intermediates are going to be less stable. So the energy barrier to form them is going to be higher, so that is going to react slower. So you're going to form less of the meta product, and you're going to form more of the ortho and para product. So CH3 or all alkyl groups in general, it doesn't matter if it's 1 carbon or 100 carbons, they're going to be OP directors. So usually you would get the para product in higher yield than the ortho product because of steric reasons, because there is some sterics here, right? But CH3 is pretty small. And furthermore, for the ortho position, there's 2 ortho positions, right? But there's only 1 para position. So statistically, you have a 2-to-1 ratio of ortho to para. So statistically, you might get more ortho substitution. In this case, you did. but usually you get more pair product because of the steric effect from the methyl, from the whatever the R group is, if a reaction occurs ortho to it. Okay, so why is CF3 a meta director? So we can do a similar analysis. Let's look at the intermediates and see which is more stable. So if substitution occurs ortho to CF3, then that's your, so now the positive is next to CF3, but that's a bad place to put a positive, because CF3, what do you know about fluorines? Is they're very electron withdrawing, right? Fluorine's the most electron negative atom in the periodic table. So that carbon's got 3 fluorines on it, so that carbon has big partial positive charge on it. So now this is bad. Right, that positive does not want to be next to CF3 because that would be destabilizing, because you got 2 positive charges next to each other. And if we look at the other resonance structures, so if we move this double bond over, then the positive is here. And if we move this double bond over, then the positive is here. But the point is, this is the key intermediate now, because that's bad. So that pathway is going to be disfavored. So you only get 6% yield there. If you do meta substitution, so if we put the nitro group here, then the positive is here. And if we draw resonance structures, now the positive is here. And if we draw the next resonance structure, then the positive is here. So if you notice, the positive skipped the carbon that has the CF3 on it. So the positive is never next to CF3, that partial positive carbon of CF3. So this pathway is going to be lower in energy because those intermediates are more stable, which is why you get such a high yield of the meta product. If you did pair substitution instead, so we take those electrons and make a bond to nitro, so positive is there, draw a resonance structure, flip this double bond over, now the positive is next to your CF3, that's bad. So that destabilizes this. So again, the intermediate is a hybrid of all of these structures. The fact that you have one of the structures where the 2 positives are next to each other makes that intermediate higher in energy, so activation energy is greater, so that pathway is going to be slower, which is why you see such a low yield for that pathway. And the other resonance forms, so then we would flip this double bond over here to put the positive there, but the point is that's the bad resonance structure. Okay, so that's why CF3 is a meta director, because you never get the positive next to the CF3. So meta is favored, but this ring still reacts slower. Why does it react slower? Because the CF3 group is removing electron density from the benzene ring, so this ring is deactivated. Right, compared to benzene. So benzene's got more electron density in it, and if it's going to react with an electrophile, right, the more electron density in the benzene ring, the faster it's going to react. So the CF3 group makes that reaction slower, but it also directs the incoming group to the meta position. Okay, so there are a lot of different OP directors. So this just lists some of the OP directors. So NH2, if there's 2 alkyl groups on nitrogen, alcohols, amides, ethers, esters, alkyl groups, right? 1 carbon or 100 carbon. Other aromatic rings, so if you had another aromatic ring attached to benzene, it would direct the next group to the ortho or para position. Alkenes, halogens, they're also OP directors, but they are deactivators. So all of the other OP directors, all of these are activators. They're going to make benzene react faster. So they're going to react faster than just benzene. The CF3, if you have one of these groups on benzene, one of the halogens, it's going to direct the next group to the ortho or para position, but the reaction is going to be slower than if it would if it was just benzene. Okay, so if you notice, most of these OP directors, so all OP directors are activators except the halogens. So if one of these is on the ring, they'll react faster. Okay, so why are halogens OP directors but deactivating? So they're electron donating by resonance, right? You can take a lone pair, and push electron density into the ring. And so that's going to make this an OP director, but they're electron withdrawing by induction because they're very electronegative. So this is a sigma bond, right? So it's going to be pulling electron density out of the ring by induction. So that withdrawal of electron density from the ring through the sigma bonds leaves the ring with less electron density compared to benzene. So the benzene ring is going to be less susceptible to act as a nucleophile. So it's going to make it react slower. Okay, so if we look at again all of these list of OP directors, if you notice, most of them have something in common. So this is where the benzene ring would be attached at in each case. So if you notice, most of them have something in common. The atom attached to benzene has a lone pair of electrons. So that's one way to identify OP directors. Right? If the atom attached to benzene has a lone pair of electrons, it's going to be an OP director. And it's going to be, well, it won't necessarily be an activator because the halogens have lone pairs, right? But they're deactivators. These are the ones that don't have lone pairs, right? So you just have to memorize that alkyl groups are OP directors, aromatic groups and alkenes are OP directors. But if you see an atom attached to benzene has a lone pair of electrons on it, it's going to be an OP director. And these are some list of meta directors. So these OP directors are in order of activating. So if you have an amine, an alcohol on the benzene ring, it's really activated. In many cases, you don't even need a catalyst to make them react. So these are meta directors, and so these are, I got these in opposite order, but going down, these are more deactivating. So at the bottom, these are the most strongly deactivating. And so if you notice what meta directors have in common, so again, this is where benzene would be attached at. So the atom attached to benzene is partial positive. So oxygen's more electronegative than carbon, so carbon's partial positive, partial positive. Nitrogen's more electronegative than carbon, so carbon's partial positive. Oxygen's more electronegative than sulfur, sulfur's partial positive. 3 fluorines, sulfur's really partial positive. Or in this case, with the nitro group, you have a full positive. Or if you have a quaternary amine, a full positive. So if the atom attached to benzene has a partial positive or a full positive charge on it, it will be a meta director. So that's one way to memorize what's a meta director. Well, you don't have to memorize these groups. You just have to look at the atom attached to it, right? If the atom attached to benzene has a lone pair, OP director. If the atom attached to the benzene has a partial positive charge, meta director. And deactivator. All meta directors, right? All meta directors are deactivators. Okay, so here I want to go through another way to illustrate why something was an OP or a meta director. So one way is to just look at resonance structures of the compound with a substituent on it. So this OH is an OP director. Why is it an OP director? Well, let's look at resonance structures. So you can take a lone pair on that, move it into benzene, and take this double bond and move it up and make a lone pair on that carbon. So now that carbon is negative, and it's got increased electron density. And then let's draw other resonance structures. So let's keep moving that around. So take this lone pair, move it down to the next bond to make a double bond there, and move the pi electrons up to make a lone pair here. So that's the ortho position, that's the pair position, has increased electron density. And now if we take the lone pair down, move it down there to make a double bond, and move this up to make a lone pair here. So now the lone pair is back at the ortho position. And then we can move it back to oxygen, move it down to make a double bond there, and then these pi electrons come back to oxygen. And so it's almost where you started at. The only difference is the double bonds have been shuffled, right? So then we could do this. And now we're back to where we started at. Okay, so if you note the ortho and para positions, right there, there, and there have increased electron density compared to the meta position. If you notice the meta position, the negative, the lone pair in the negative is never at the meta position. So if you have, so the OP positions have increased electron density. So if you do electrophilic aromatic substitution, so if you have an electrophile like nitro that wants electrons, where is it going to react at? It's going to react where the most electrons are at. The OP positions have increased electron density. Positive is never, the negative is never at the meta position, so the nitro is not going to be naturally attracted to the meta position. It's going to be attracted to the ortho pair positions. So similarly, why is the nitro group a meta director? Well, let's just look at resonance structures of the nitro. So it's a positive, so it wants electrons. So we're going to push electrons, pull electrons out of the ring. So make a double bond to nitrogen and move these two electrons up onto oxygen. So now that carbon is positive. And if we draw more resonance structures, so move the next double bond over, then now that carbon is positive. Move the next double bond over, and now that carbon is positive. And then we can take this lone pair and move it back to there, and move this pi bond back to there to remake your benzene. And then if we shuffle the double bonds in benzene, then now you're back to where you started at. So if you notice, the ortho, para, and ortho positions have decreased electron density. So if you have an electrophile that wants electrons, where is it going to react at? It's going to react where the most electron density is at. It's not the ortho para positions, because those positions have some positive charge density on them. So it's going to react at the meta position. Right, so the nitro group is a meta director because it removes electron density out of the benzene ring, and in particularly that creates positive charge density at the ortho para positions, but not the meta position. So the meta position has the most electron density. That's where chlorine is going to react at. Okay, so lastly in this lecture, let's look at, so what happens if you put a third group on the benzene ring? So the CH3 is an OP director. So that wants to put the bromine there and there, and the para position to CH3 is blocked already. It's got a nitro there. And the NO2 group is a meta director. Let's put that in a different color. So it wants to put the bromine here and here, so they both want to put it at the same spot. And of course those two positions are equivalent to each other. So in this case they both direct the bromine to that spot. So that's where the third group goes. Okay, so in this case, so is this an OP or a meta director? Well, how do you know? It's got a lone pair of electrons on the atom attached to benzene. It's an OP director. So it wants to put the bromine here and here, ortho to it. The para position is a block because it's got a chlorine there. And what about the chlorine? It's got a lone pair. It's an OP director. So it wants to put the bromine there and there. So now they don't want to put it at the same spot. And of course, para to chlorine is already blocked because it's got the nitrogen there. So now they're not working together. They're working opposite of each other. So which one wins? Well, the most activating group always wins. And so if you remember, this is a deactivator, right? But this is an activator. So this wins. So the nitrogen wins. So your major product would be it would put the bromine ortho to the nitrogen. And of course on the here top or bottom, those are equivalent by symmetry, so it doesn't matter where you put it, it's the same molecule. Okay, so in this example, so 2 methyl groups, Opie directors. So let's see, so this methyl group, let's just call it red. So it wants to put the nitro group here, here, or here. And the other methyl group is an OP director, so it wants to put it there, there, or there. So again, they're directing it to the same spot. And of course, this position and that position are the same. So there's 2 possible products, right? Nitro. So we'll call this A and B. So we could put the nitro at A or B, they're equivalent. Or if we call this C, we could put the nitro here at C. And so we make 98% of this and very little of this. So why do we get so much of this product when the methyl groups are directing them to the same exact spot? Well, it's for a steric reason, right? This is sterically crowded. Because of the 2 CH3 groups, so it kind of blocks that position, and it's going to then force the nitro group to go to A or B. So that would be your major product. So yeah, usually doing the substitution between 2 groups is much more difficult for steric reasons. Okay, we'll stop there.